Sure. And there is one thing that I was saying to Professor Sato, is that if you check the proof up to this part here, there is nothing really relevant. Up to here, there is nothing really relevant on self-similar processes. In fact, if you do the same construction for any process, you will get up to here without any problem. Okay? But from here to here is the key step, because we get rid of this dependence on the starting point. And this dependence on the starting point, we get it from here by the construction. And that is just really using the scaling property. Okay? And here is where the scaling property is really, really important. So we get something that is not depending on the starting point. Okay? And we get this. And from there we get the independence of the stationary, of the increments. Okay? And let me check if I have it here. This doesn't depend on x0. It's just coming from here. Okay? Just try to write it. You will see it is almost straightforward. Okay? But it's this fact that is the most important in all this proof. Okay? And in fact, this proof that I wrote here works essentially for any dimension. This works for dimension. I prove it for dimension 1 when the process is strictly positive. Okay? But I will write at the end of the course the general proof, and in fact there we will see that from here we will go to here by just taking the angle of the process. Okay? And so when we go to a bigger dimension, here we will have something that depends on the past only through the angle of the process at time t. Okay? So this process that is here, in dimension bigger, okay, it's a process that will have a similar property of independent increments, okay, and stationarity, but just the increment will depend on the angle of the process at this time. Okay? That is what makes appear what I call Markov Additive Processes, which is the dependence of the generalization of Lévy processes, okay, when the jump structure or the movement of the process depends on some environment. That environment will be given by the angle of the self-similar process. Okay? Is there any question about this? Okay, if there are no questions, then I move to some precise results on stable processes. I want to make some explicit calculations for stable processes. In particular, what I want to do is to determine the process that is related to a stable process. Okay, the Lévy process that is related to a stable process. So we move into our next sections, which is some explicit calculations for stable processes. For stable processes. By a stable process, we mean a Lévy process with the scaling property that for all C positive, C times xt, C to the minus alpha, T positive, has the same law as xt for T positive. Okay? This when x0 is equal to 0 and alpha is in between 0 and 2. Okay? In this case, we say that x is an alpha stable process. Okay? In dimension 1, well, this scaling property in dimension d, okay, is such that the characteristic exponent psi should satisfy that psi k lambda is equal to k alpha psi lambda for all lambda in Rd and k positive, and psi is such that exponential of I lambda xt is equal to exponential of minus t psi lambda for lambda in Rd. Okay? So it's just the property, the scaling property that I wrote here, okay, that gives that the characteristic exponent should have that property. The characteristic exponent should have this property. Okay. When the dimension is 1, the characteristic exponent can be written as this minus c lambda to the alpha times 1 minus delta sine of lambda. This is the sine function tangent of pi alpha divided by 2, and this happens in the cases for lambda in R, and this for alpha in between 0 and 1, or alpha in between 1 and 2. For alpha equal 1, it is equal to minus c lambda 1 plus I delta 2 divided by pi sine of lambda log of absolute value of lambda when alpha is equal to 1, lambda is in R. And then it's minus sigma square lambda squared divided by 2 lambda in R when alpha is equal to 2. Okay? So this is a Brownian motion, this is a Cauchy process, as this is an alpha stable process. Okay? Any other alpha stable process. For the proof of that, of course, I will not do it. I can just refer to Sato's, Professor Sato book. Yeah.
First line, no minus first line.
First.
No, above that.
This one.
Yes.
Yes. Oh, there is no minus here because of how I wrote it. Yes. Thank you. Yes. Mm-hmm. Thank you. Okay. So when alpha is equal to 2, x is a Brownian motion. Okay, so it is continuous. Okay, and when alpha is in between 0 and 2, then x has no continuous part. Okay, so all the movements of x are given by the jumps. Okay, and x has a Lévy measure that is given by yes, by dx given by a constant c plus dx divided by x to the 1 plus alpha for x bigger than 0 when alpha is not equal to 1, and c minus dx absolute value of x to the 1 plus alpha when x is smaller than 0. Here again, alpha is not equal to 1. Okay. Here I must say that when this is in general, okay, but if alpha is equal to 1, the self-similarity only holds if delta is equal to 0. Okay. If not, it is not self-similar. Okay? That's a case of a symmetric Cauchy process. Okay, and when alpha is equal to 1, the Lévy measure takes the form dx absolute value of x to the square when alpha is equal to 1, and that is for all x in R. Okay, it's just to settle the notation. This delta is what is called the skewness parameter. Okay. and the constant c that is there is given by minus c plus c minus gamma of minus alpha and cosinus pi alpha over 2. Okay. And there is rho, which is the probability that x1 is strictly positive. Okay. Notice that that doesn't depend on t. Okay. And rho can be written in terms of delta and alpha as 1/2 plus 1 alpha pi arc tangent, so inverse tangent of delta tangent of pi alpha divided by 2. Okay, you can check all these details in Professor Sato's book. Okay. This process is self-similar, but is not positive. Okay, so I will be considering another process, which is the process killed at the first passage time below 0. So yt, let yt be x killed at the first passage time below 0. So if we denote by t0 minus the first time where xt goes below 0, we take yt to be xt if t is smaller than tau 0 minus, and 0 if t is bigger or equal than tau 0 minus. Okay? So if we have a process that starts from x, okay? So just recall that x issued from 0 from x has the same law as little x plus x, where x is issued from 0. Okay? So starting a Lévy process from little x is just shifting the path to x. Okay? Okay, so we start from a little x that is bigger than 0. So this process, when alpha is different from 2, we'll have a lot of jumps, many little jumps, a few that are bigger, and then eventually it will jump to some level below 0, okay? And instead of continue observing the path of x, we stop the process and we stick it to 0. Okay? And that sticking to 0, we understand it as sending the process to a cemetery state. Okay? So whenever it goes below 0, we kill the process. Okay? So the process y has this path. Okay? So it is important to say that x tau 0 minus, so which is the limit as t grows to tau 0 minus of xt, this is strictly positive if and only if pi of minus infinity 0 is bigger than 0, okay? But pi of minus infinity to 0 being bigger than 0 is equivalent to say that C minus is strictly positive. Okay. Okay. And this if alpha is in between 0 to 2. When alpha is equal to 2, the process is a Brownian motion, so it will hit 0 continuously. Okay? If C minus is 0, the process will hit 0 continuously. Okay? In all the other cases, the process will hit 0, will go below 0 by a jump. Okay. And I would like to prove the following theorem, which is that let psi star be the Lévy process associate to Y via Lamperti's transform. Okay, so Y is the exponential of psi time change. Okay, psi star. Okay. So we have that psi star has the following characteristics. Okay. The lifetime of psi star follows an exponential distribution of parameter C minus divided by alpha. Okay, so if C minus is 0, the exponential is infinite almost surely. Okay, C minus equal to 0 means the lifetime, which is C, is equal to infinity almost surely. Okay? That's the first characteristic. The second characteristic is the Gaussian term. Is sigma equal to 0 if alpha is smaller than 2. Okay. And here I must say that alpha will be always smaller than 2. Why I removed the case alpha equal 2? Because the case alpha equal 2 was deal yesterday. Alpha equal 2 appears in the Bessel process example in lecture 2. Okay. Okay, so in this theorem is for alpha smaller than 2. Okay. So when alpha is smaller than 2, there is no continuous part. So there is no continuous part in the Lévy process that is behind this table because of Lamperti transformation. Remember, Lamperti transformation does not change the path. Okay? So I'm not adding discontinuities or continuities by making a time change. Okay? So if there is no continuous part in y, there is no continuous part in psi star. Okay? And the Lévy measure is given by pi star dy divided by dy is equal to c plus exponential of y minus 1 to the 1 plus alpha, indicator y is bigger than 0, plus c minus exponential of y, absolute value of exponential of y minus 1 to the 1 plus alpha, indicator y is smaller than 0 for y real. Okay. There is more in this theorem. We have that if C plus and C minus are taken as C plus gamma 1 plus alpha sinus alpha pi rho. Rho is again the positivity parameter, okay, divided by pi, and C minus is equal to gamma 1 plus alpha sinus alpha pi 1 minus rho divided by pi. Okay. For rho in between 0 and 1, then rho is still the positivity parameter, and more important, the characteristic exponent of psi star at 1 when 1 is smaller than the lifetime. Okay? So in order to be able to determine this exponential, I need the process to be alive. This is equal to exponential of minus psi of psi star of lambda, and psi of psi star of lambda is equal to a quotient of gammas, gamma alpha minus I lambda divided by gamma of alpha 1 minus rho minus I lambda times gamma 1 plus I lambda divided by gamma 1 minus alpha 1 minus rho plus I lambda. And this happening for all lambda real. And the fact okay, so it can be written in that form. Okay. But the fact that we wrote that as a product of two functions is more than a coincidence, this is coming from the Wiener-Hoff factorization. I will recall that later for those of you who are not familiar with that. Okay? But in fact, the Wiener-Hoff factorization tells us that the characteristic exponent of a Lévy process can always be written as the characteristic exponent of the product, as a product of the characteristic exponent of two subordinators. One is the upward ladder height subordinator, so describing the supremum of the process. And the other one is the downward ladder height process, which is describing the infimum of the process. Okay? So this is for the upward ladder height, and this is for the downward ladder height process associated to psi star. Okay? But if you don't know that for the moment, that is not an issue. But this is important because for a lot of time, for a long time, there were just a few examples of Lévy processes for which the Wiener-Hoff factorization was known explicitly. Okay? So thanks to this work of Lamperti, this representation, Cipriano, Pardo, and Kuznetsov were able to make this explicit, okay, and find another example of an explicit Wiener-Hoff factorization. Okay. This is. Is there any question with respect to the statement of the theorem? No? Okay. 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 So to prove this theorem, what I really need to do is to prove that the lifetime has a parameter of that it is exponential. We know it from the Lamperti transformation. Okay, we need to determine the parameter. Okay, so that is one of the things that we need to do, and then we need to check that the Lévy measure is of this form. Okay. I don't need to check that sigma is equal to 0 because we know there is no continuous part in the process. Okay? And well, there are several ways to do it. One of them is by working with the infinitesimal generator, but I don't want to do that. I prefer to work with the jumps of psi star. Okay? We know that the jumps of psi star, so it's form a Poisson point process with intensity pi dx. Okay? That means that if we count the number of points t positive such that t and psi star t minus psi star t minus, okay, and these are in some set B, for B being any Borel set of 0 infinity times R minus 0, okay, this random variable follows a Poisson distribution with parameters, the integral with respect with Lévy measure on 0 infinity, and the integral with respect to pi dx on r minus 0 of the indicator of Sx being in B. Okay? So this is a Poisson random variable, and the parameter is just the area under this measure of B. Okay? And there is something that is very important for me, is the compensation formula. Which tell us, okay, that pi is the unique, here I should write pi star for the Lévy measure of psi star. Yeah, pi star, okay, is the unique measure such that the expected value of the sum of jumps up to the lifetime of any function of time and of the jump okay, this expected value is equal to the expected value of the integral between 0 and the lifetime dt, and the integral with respect to pi star dx for x in r minus 0 of f of t and x, okay, for any f positive measurable such that f of 0 is equal to 0. Okay? So if we we determine the expected value of jumps that satisfy a condition, okay? That is just the same as the expected value of the area of that. Yes, that's correct. Yeah. Mm-hmm. Of that.
Alphabet for the lifetime.
Sorry?
Let's the alphabet for the basic.
C. So this is
C.
yeah, theta. Okay, and this is the first time where psi t is equal to minus infinity. Okay, it's just the lifetime of psi. I'm saying there is something missing here. No, that's okay. Yeah, is that. Okay, so the Lévy measure, okay, is the unique measure that satisfies this identity, in fact. Okay. And that in fact happens for any Lévy process. Okay? And in fact, you can do a bit more. You can do, instead of putting here a function just of the jump, you can put something that depends also on the past of the process before time t. Okay? So we can, this function, the formula will still be true if we take something that is random, okay, but depending on the past of the process up to time t, the strict past. Okay. So I'm gonna write this in terms of x, okay? And then using the properties of x, then I'm gonna find this and the time change. So if I take the sum of ft psi star t minus psi star t minus, this by construction of psi star is just the expected value over the sum of ft and then the log of y bt over y bt minus, okay? And this on the event where y bt is different than y bt minus, okay? And bt is smaller than the first passage time below 0. So remember that psi star by Lamperti transformation is the log of y bt or y0, okay, where bt is the inverse of y s to the minus alpha 0 to s y u du bigger than t, and that yes, tau 0 minus is the lifetime of y, okay? Just by the way we constructed y, okay? So y dies at the first passage time below 0 for x, okay? Okay. So if we take the difference of this guy and this guy left limit, we just get the quotient of y bt divided by y bt minus. Okay. Okay. One point that is very important here is that, again, that bt, okay, is a continuous function, okay, because it's the inverse of a continuous function, okay. So every discontinuity point of y corresponds to a discontinuity point of psi, okay. I am not adding or removing discontinuity points in these two guys, okay. I'm just observing them at a different scale of time. Okay? So if I add all of them in the lifetime, I add all of them in the lifetime of the other guy. Okay? So this is equal then to the expected value for t smaller than tau 0 minus of f of the integral from 0 to t of y s to the minus alpha ds, and then the log of ys yt over yt minus on the event where yt is different from yt minus and yt is strictly positive. Okay? So it's just this. If this is a time where there is a discontinuity for this process, okay, it is then this time is a discontinuity for this guy. Okay, just by inversion. Remember, t is equal to the integral up to bt of ys to the minus alpha ds. Okay, because they are just inverse functions. Okay. So I change the scale of time from here to here. Okay, and make a change of variables. Okay, but because I'm observing y up to the first passage time below 0, up to its lifetime, this is the same as observing x everywhere. Okay? So I can change into x. Okay? But x is a stable process. Okay? So I have the compensation formula for the stable process. Okay? So by the compensation formula, this will be equal to the expected value from 0 to the first passage time below 0 of the integral in r minus 0 pi dx. This is the Lévy measure of the stable process. Okay, maybe I should write it as a capital X just to clarify. Okay, and then there is an f of the integral from 0 to t of xs to the minus alpha ds, and then there is the log of 1 plus y divided by xt minus, yes, this is in the event where xt minus plus y is bigger than 0. Okay, so this term here is just coming from writing here xt is equal to xt minus plus xt minus xt minus. Okay, this is the jump that I am counting. Okay, and so I replace the jump by an integral with respect to y. Yeah. Okay, and then this is something that is depending on the past. This is something that is depending on the past. So I can use the compensation formula, okay? Okay. So I will write this as 1 plus 2, where 1 is pi, the restriction of pi to y positive, okay? And 2 is pi, the integral of pi restricted to y smaller than 0. Is everything clear so far? Or in this equality at least? Do you believe it?
Yeah.
Koji? Kasu?
I think that we can omit
The indicator?
that the xt positive because t is less than tau 0 minus.
Yes, we don't need
You
it.
don't omit it.
I don't omit it, just to remember here that I shouldn't go below 0 because there will be a problem here. But yeah, it's just to be sure that the log is well defined. But of course, it's well defined because of this, indeed. But there is one reason I am keeping it there, because here is t. Okay. By the Lévy, because this is the Lévy measure, and this is countable. Okay, these continuities are countable. Then I can remove the left limit by the right limit, and then I need this. Okay, yes, you're right. So this is equal to the expected value from 0 to tau 0 minus dt indicator r minus 0 pi x dy f integral 0 t xs to the minus alpha ds and the log of 1 plus y over xt indicator xt plus y is bigger than 0. Okay, so I keep track of this indicator that is here, okay, just because later I will change to xt instead of xt minus, because I'm integrating with respect to Lévy measure. Okay, so I don't see the discontinuity points in this integral. Okay? Okay. Where should I write now? Okay. So the integral 1 is just the expected value from 0 to tau 0 minus of dt indicator y being bigger than 0 c plus dy y 1 plus alpha, okay, f of ct is the integral, and then log of 1 plus y xt indicator y plus xt is bigger than 0. Okay, I just replace the expression of pi, okay, because I'm taking the restriction of y bigger than 0. Okay, then I make a change of variables to be c equal to log 1 plus y divided by xt. Okay, if I do that, I will get that dy is equal to xt exponential c dc. Yeah. So this becomes the expected value of the integral from 0 to tau 0 minus of dt xt to the minus alpha, the integral for c being bigger than 0, just because y is bigger than 0, okay, so c is bigger than 0, and then I have a dc times c plus, then ec minus 1 plus alpha exponential c f of the integral from 0 to t x's to the minus alpha ds, and then c, and then indicator. the indicator is here now. Okay? This indicator here is becoming this one. Okay? Okay. Dun, dun. Then I just make a change of variables s equal to the integral, or u equal to the integral from 0 to s equal to the integral from 0 to t of x u to the minus alpha du. Okay. So this dt is just the differential of the s. So this is the expected value from 0 to now theta, the lifetime of ds. This xt is going away because of the change of variables. And this is what I wanted to prove here for x positive. Are we happy with this calculation? Okay. Do you have a question? Look like. Yeah? Okay. Okay. So, if I do this with the first term, I get the Lévy measure on the positive part, okay? I do the same thing for the second integral. I get the Lévy measure on the negative part, okay? And then I get the expression, the full expression that I need here. Okay, and then I'm done with that part. Okay. Well, I like this calculation because it's something that can also be done in a general setting. Okay, for a general d-dimensional stable process. Of course, everything becomes nastier because we will be working with a d-dimensional measure. But, other than that, the same calculation works in general. Okay. Okay. So this finishes the proof of the third claim. Okay, let me prove the first one. And here again, the compensation formula will be very useful. So, proof of one. For that, we need a lemma, which is that the expected value starting from 1 of f of tau 0 minus, actually, yeah, from any x, this can be written as the expected value of the integral from 0 to infinity in dt of f of t of the expected value of pi of minus infinity xt for t is smaller than tau 0 minus. Okay. For any f from 0 to infinity into 0 infinity measurable. Okay. This is a consequence, again, of the compensation formula. And the reason for that is that tau 0 minus, okay, tau 0 minus will happen at the first time where the process jumps from a position above 0 into a position below 0, okay, and instantaneously that happens with this rate. It's easy. I will suggest this as an exercise. And there is one important consequence, which is that the expected value starting from x of the integral between 0 and infinity of pi okay. So this implies that the expected value of the integral between 0 and infinity of pi of minus infinity xt when t is smaller than tau 0 minus dt is equal to 1. Okay? Because this function that is here is just the density of this random variable. Okay? But this is the same as writing that the expected value of the integral from 0 to tau 0 minus of pi of minus infinity xt dt is equal to 1. Okay? But who is this quantity here? Pi of minus infinity x is just equal to c minus divided by alpha of x to the alpha for x, absolute value, for x negative. Okay? For x positive. Let me write it as it is. Sorry. Here there is a mistake. I think. Yeah. Sorry for that. Okay. Okay. This quantity that we have here, okay, this quantity is equal to this one. Okay. Now remember that the lifetime of psi star is such that it has the same law as the integral from 0 to tau 0 minus of xs to the minus alpha ds. Okay? So this integral that we have here is in fact equal to the expected value of the integral between 0 and tau 0 minus of xs to the minus alpha ds times c plus over alpha, and this is equal to 1. Yeah? So this guy here is just c times c to the alpha. So we have that the expected value of c times c minus divided by alpha, this is a c minus, is equal to 1. Yeah? So the expected value of the lifetime is equal to alpha divided by c minus. Okay? So this is equal to 1 over the parameter of the exponential. Okay? And that is the main, that is the proof of the second claim, or the first claim. Is that okay? Okay. This is an exercise that we can check tomorrow if you want. And what else? Yeah, from if we believe this, then we get this immediately. Okay, and it's just identifying this this Lévy measure with this quantity here. Okay. Okay. Okay, let me just finish the lecture by describing two more processes related to this table. The first one is y up arrow, which is x condition to stay positive. Okay? So this one is the process obtained by making tau 0 go to infinity. Okay? And then there is a second one, which is y down arrow, which is x condition to reach 0 continuously. So this one is the one that we obtain by conditioning this guy to go to 0 from the left. Okay? Whatever this means. Okay? I will describe that. Okay? But these two processes are self-similar. Okay? Because the conditioning will not change the scaling property. Okay? And then they are the Lamperti transformation of some Lévy processes. Okay? So Y oparo can be seen as the Lamperti transformation, so let me write it as LT, of a process psi oparo, and Y down arrow can be seen as a Lamperti transformation of a process psi down arrow, okay? And I would like to know who are these two processes. Psi up arrow and psi down arrow, and how are they related to psi star? Okay, so in particular, can we find the characteristic measure, and can we find the characteristic exponent? Okay. The answer is yes. And it is closely related to the expression I delete for the characteristic exponent. Okay? We will see that these two processes are obtained as a Girsanov transform of this process. Okay? Okay. To make this statement precise, is that the law of Y oparo is that is obtained by the conditioning so we have that P oparo of let's say starting from X of any function of xs for s smaller than t is the limit as q or as t goes to infinity, or as u tends to infinity, of the expected value starting from x of f of xs for s smaller than t, conditionally on the first passage time below 0 to be bigger than t plus u. Okay? Okay. And by doing this conditioning, one can verify that the law of this process starting from x on the filtration up to time t is absolutely continuous with respect to the one of the process x killed at the first passage time below 0. And the density is xt to the alpha rho hat, rho bar, divided by x to the alpha rho bar of px restricted on the event ft indicator t is smaller than tau 0 minus. Okay? So what I'm claiming here is that this limit is well defined, okay? And that what will appear from this conditioning is a density of this form. Okay? And this uses that the probability that is appearing here behaves as t goes to infinity like a constant that depends on alpha and on rho hat that is known explicitly, but I will not explicit at the moment. And then an x to the alpha rho bar divided by t to the minus rho hat, rho bar, t to the rho bar, okay, which can be seen in Bertoine's book. Okay? And this is a consequence of the fluctuation theory of Lévy processes. Okay. Okay. So this term that is here is in fact the one that we have here, okay? And it will appear inside this because of the Markov property, okay? And this is also a consequence of a more general result on conditioning of Lévy processes to stay positive. Okay. Okay. In fact, this absolute continuity relation that we have here, okay, can be translated into an absolute continuity relation for the Lévy processes that are behind. Okay. The absolute continuity relation star holds true for stopping times and this is a consequence to the of the optimal stopping theorem. Why are we having the optimal stopping theorem, which is something for martingales, because here we have a martingale, in fact. Okay, so we pass, we apply the martingale property on random times. And we can transfer this absolute continuity in absolute continuity for random times, okay? And in particular, it holds for the random times appearing in the Lamperti transformation, okay? So, in particular, for the random times, Bt equal to the inverse okay. So we define a new probability measure P of Paro on f of Bt, which is equal to x in Bt alpha rho hat, rho bar, x times p of x restricted to f on Bt intersection Bt is smaller than tau 0 minus. Okay? But what I am doing here by time changing this, okay, this time change is the one appearing in the Lamperti transformation. Okay? So the law that I get here is just the law of the process that is associated to y oparu via Lamperti transform. Okay? So this is the law of psi oparu. Okay? Okay, so I do a conditioning, I get a new probability measure. That probability measure is related to the original one via this density. Okay? And when I do the time change that appears in the Lamperti transform, on the right-hand side, I get the Lévy process that is behind the stable killed at the first passage time below 0, so psi star. And at the left-hand side, I get the law of the process, of the Lévy process that is behind the stable process conditioned to stay positive. Okay? So, by doing this, and plugging all the bits, what I get is that P oparu up to F Bt is equal to exponential alpha rho hat psi star, and then P, where P, or let's say P star, is the law of psi star, and this is true up to the filtration up to time Bt. This is for time t. There is something that is important here, is that this process has a finite lifetime. Okay? But this one, because it's a process conditioned to stay positive, okay? If this process has an infinite lifetime, this one here should have an infinite lifetime, okay? Because we will observe the whole path of the process. We will not kill the process at an exponential time. Okay? So under this process, we get a process that has an infinite lifetime. This one has is carried by the paths that are killed at an exponential time. Okay? So this absolute continuity relation just holds locally. It will not hold over the whole interval of life. Okay? Because they are orthogonal, in fact. Okay? Okay. This was a bit fast, I know, but really what we need here is just this estimate. Okay? We need that we can put the limit into the integral that is here, okay? But then once we know we can do this, the rest just follows, okay? And this has been studied by Chomont and Doni. In the paper of Lévy processes, condition to stay positive. Okay, so there one can check that this limit is well defined. Okay, and in the particular case of a stable, it becomes this. Okay, and then I apply the time change and I get the rest. Okay, and something similar happens for the other process, for the process condition to go to hit zero continuation. But I state that tomorrow. I think it's better. Are there any questions or comments? Complaints?
Maybe rho bar equals to 1 minus rho v.
Yes. Thank you. Yeah. Okay, so tomorrow I will give a few more details about this, about the case where the process is conditioned to hit 0 continuously. And then I will work on the exponential functionals of Lévy processes. Okay? And maybe a little bit on entrance laws. Okay, thank you.